Hi, everybody. In this video, we are going to talk about the rules for exponents. First, a little bit of vocabulary. If we have a couple of numbers written like this, the bottom number is called the base, and the number which is written above it and a little bit to the right and a little bit smaller is called the exponent. And in this example here, this would be read 5 to the third power. So power is another word which is used when we're talking about an exponent. All right, so what does this mean? So when the exponent is a natural number, and the natural numbers are just 1, 2, 3, 4, 5, 6, etc. They're also called the counting numbers. It simply tells you how many times to multiply the base with itself. So for example, 5 to the third power means we should multiply 5 with itself 3 times. So we would have 5 times 5 times 5, which would be 125, because 5 times 5 is 25, and then 25 times 5 is 125. 2 to the sixth power means 2 times 2 times 2 times 2 times 2 times 2. You can see we have 6 2's here all multiplied with each other. And that would give us 64, because 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64. Okay, I'm glad I got that right over there. If we have something to the first power, then it's just itself. So for example, 8 to the first power is just 8. And this rule applies even when the base is a negative number. We're going to, in the next video, we'll talk about what happens when the exponent is a negative number. Right now, we're just defining what it means to have a base raised to an exponent where the exponent is a natural number. So going back to this example, we have -4 to the third power, which means -4 times -4 times -4. You can see that's we have it multiplied 3 times here. So -4 times -4, well, a negative times a negative is positive. So that would give us a positive 16. And then positive 16 times -4. Well, a positive times a negative is negative. So, and 16 times 4 is 64. So this would give us a -64. Now, a lot of students think that if the base is negative, then the answer must also be negative. It was in this case, but that's not always true. So for example, if we have -4 to the fourth power, let's see, -4 times 4 is positive 16. If I multiply a positive by a negative, then I would get a negative. So positive 16 times -4 is -64. That's where we got last time. But now I have -64 here. If I multiply by a negative again, well, a negative times a negative is positive. So now I'm going to get a positive number as my answer. And 64 times 4 is 256. That would be a positive 256. So that's my answer over here. So it changes every time. If this is negative, if I multiply it by a negative again, I would get a positive. If I multiply by another negative, I'd get a negative. If I multiply by another negative, I would get a positive. It keeps going negative, positive, and so on. So if the base is a negative number and the exponent is odd, then the answer will turn out to be negative. If the base is a negative number, but the the exponent is an even number, a number which is divisible by 2, and an odd number is a number which is not divisible by 2. If the exponent is an even number, then it'll turn out to be, we'll get a positive answer. All right, so let's move along here. So now we know what to do with an exponent, which is a natural number, 1, 2, 3, etc. What happens when we multiply two terms together? So when multiplying terms with the same base, add the exponents. So here's how we would write that algebraically. If we have some number a, so a just stands for a number, and we raise it to an exponent of b, so b is our exponent, and then we multiply that by another term, a to the c power. So the base is the same as it was before here, but now we have another a different exponent, or it could even be the same exponent, then for our answer, we would get that same base that we had in both of these terms here, raised to the power of b plus c. So this will make a little bit more sense as we go through these examples. Let's see where this rule comes from in the first example, and then we'll use that rule to work out another couple of examples. So 4 to the third times 4 to the second. What would that be? And you know what? Let's just forget about this rule for a second. Let's just do this, and then we'll see where this rule comes from. So 4 to the third means 4 times 4 times 4. Okay, and then we have times. So we have another multiplication symbol right over here. So we're multiplying 4 to the third by 4 to the second. So now we have two more 4s. Okay, there it is, 4 times 4. So you can see that all together here we have 5 4s. 4 times 4 times 4 times 4 times 4. So we have 5 4s there, and that would be 4 to the fifth power. And if we just multiply all these 4s out, we would get 1024. Okay, but you can see, if you didn't want to actually write all of these 4s out, how could you have figured out that there would be 5 altogether? Well, you know that there are 3 coming from this term over here, and there are another two 4s coming from this term over here. So how many 4s do we have altogether? It would be 5 4s, because 3 plus 2 is 5, right? So using this rule, we could have just said, okay, well, if I have 4 to the third times 4 to the second, I'm going to have 3 plus 2 4s. Well, what is 3 plus 2? That's 5. So altogether, I'm going to have 5 4s, and here it is all written out. Okay, next example, z to the 8th times z to the 3rd. Well, again, instead of writing it all out, we could just say to ourselves, well, okay, I have 8 z's coming from the first term, and I have 3 z's coming from the second term. So how many z's am I going to have all together? Well, I'm just going to have 8 plus 3 z's, which is 11. So my final answer will just be z to the 11th power. Okay, and we're not going to be able to say that this is equal to some number, because we don't know what z is. Like over here, we knew that our base was 4. So we were able to say 4 times 4 times 4 times 4 times 4 is 1024. I can't say that over here because I don't know what z is. So I'm just going to have to write my final answer as z to the 11th power. But again, if you forget where this rule comes from, you can just work it all out, and you can see that we have 1, 2, 3, 4, 5, 6, 7, 8 z's coming from the first term, times another 1, 2, 3 z's coming from the second term. So all together, we have 11 z's. And by the way, I'm using a dot over here to represent multiplication. It's just another way of writing multiplication, so you should get used to that. Sometimes you'll see me writing an X to represent multiplication. Sometimes you'll see me writing a dot to represent multiplication. It means the same thing, okay? All right, now over here, what would w to the 470th power times w to the 85th power be? Now, this is an example where the numbers are really large, and it would take a really long time to actually write out 470 W's and then another 85 W's and then count up how many W's we have all together. But we can use this rule over here so that we don't actually have to write it all out. We know that we're going to have 470 W's from the first term, plus another 85 W's from the second term. So if we were to write it all out, then altogether, how many W's would we have? We'll just add 470 and 85. And that would be, 555. So we would get w to the 555th power, okay? So that's the answer over there. All right. Now over here we have a negative exponent. We didn't even define what that means yet. I only told you what the rule was for an exponent, which is a natural number, 1, 2, 3, and so on. We didn't even say what the rule was for a negative exponent, right? And a lot of people get confused when they look at a negative exponent, because with good reason, because we said that an exponent means you're multiplying the base with itself that many times. What does it mean to multiply 6 with itself negative 12 times? Okay, right? That's just nonsense. It really it doesn't mean anything. So we're going to have to define what it means to have a negative exponent. But we're not going to do that in this video. We're going to do that in the next video. Right now, I'm still going to show you an example with a negative exponent, just to tell you that this rule over here still works when we do have a negative exponent, and I will hopefully convince you of that in the next video. For now, just take my word for it that we can have a negative exponent and still use this rule. So let's see what that would look like. Using this rule over here, we would say that 6 to the 10th power times 6 to the negative 12th power is 6 to the 10 plus negative 12th power. So what is 10 plus negative 12? Well, that's the same thing as 10 minus 12. And 10 minus 12 is not 2, be careful. 10 minus 12 is negative 2. So this would be 6 to the negative that sounds weird, negative second power. Okay, 6 to the power of negative 2. That sounds better. Now, what does it even mean to say 6 to the power of negative 2? We'll talk about that in the next video, okay? But I don't want you to think that just because there was a negative exponent over here, or just because you see a negative exponent in the problem, the answer will also necessarily have a negative exponent. That's not always going to happen. We could very easily come up with another problem where we still see a negative exponent in the problem, but the answer will not have a negative exponent. So for example, 6 to the 12th times 6 to the negative 10th power, that would be equal to 6 to the 12 plus negative 10th power. 12 plus negative 10 is the same thing as 12 minus 10, and 12 minus 10 is positive 2. Okay, and we do know what this means. 6 to the power of positive 2 just means 6 times 6, which is 36, okay? So nothing strange going on over here. All right, so let's just continue. And let's talk about what happens when we divide. Okay, so when dividing terms with the same base, subtract the exponents. So if we have a number a, which is raised to the power of b, divided by the same number as our base a, raised to the power of c, then to find the answer quickly, we could just do that base a raised to the power of b minus c. So we could just subtract these numbers, subtract the exponent in the numerator by the exponent in the denominator, and then use that as the new exponent. So that's the rule. Let's look at this example here to see where that rule comes from, and then let's use that rule for these other problems over here. So if we have a problem 4 to the 8th power divided by 4 to the 5th power, and I'm using the fraction bar here to represent division, what does that really mean? That means that in the numerator, I have 4 multiplied with itself 8 times. So I have a string of 8 4s. 4 times 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 4. In the denominator, I have 4 to the 5th power. So that means 4 times 4 times 4 times 4 times 4. Okay, so I have 5 4s in the denominator. Well, how can I simplify this? I could simplify this by writing, here I have just one big messy looking fraction. this is actually equivalent to, it's the same thing as a whole bunch of fractions multiplied with each other. So this is the same, this messy fraction is the same thing as 4 over 4, which I wrote over here, times another 4 over 4, times another 4 over 4, okay, times another 4 over 4, times another 4 over 4, and then I ran out of 4s in the denominator, so these 3 4s which were left over in the numerator, I'm just going to write those out by themselves, not in a fraction, just as themselves. So I have 4 over 4 times 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 4 times 4 times 4. Okay, these 4s over here don't get anything in the denominator because we ran out of 4s in the denominator. Now, what is 4 divided by 4? 4 divided by 4 is just 1, right? So all of these 4 over 4s are really just 1s. And you can see I wrote over here, instead of writing 4 over 4, I wrote 1. So 4 over 4 is 1. 4 over 4 is 1. So we have 1 times 1 times 1 times 1 times 1. That's all of these guys over here. And then we still have these 3 leftover 4s over here. Now, 1 times 1 times 1 times 1 times 1 is just 1. And 1 times 4 times 4 times 4, or 1 times anything, is just itself, right? So 1 times 7, for example, is just 7, isn't it? 1 times 8 is just 8, right? So 1 times 4 times 4 times 4 is just 4 times 4 times 4. We don't even need to write all of these 1s over here. So now all of this has simplified to just 4 times 4 times 4, which is 4 to the 3rd power, because we had these 3s left over, these 3 4s left over. In other words, another way of saying that is that these 4s over here canceled each other out. Really, what we mean by saying that they canceled out is they became 1, and anything times 1 is just itself, so we don't even pay attention to the 1s. So all these, they canceled each other out until we had just these 3 4s left over, and that's why we got 4 to the 3rd power. Okay, 4 times 4 times 4, which is 64, okay? And now that we've done all of that work, we never have to do it again. Because from now on, whenever we get a problem like this, we can think about it in the following way. We can say to ourselves, okay, I have 8 4s in the numerator, and I have 5 4s in the denominator. How many 4s are going to be left over? Well, how am I going to figure that out? I could say that the number of 4s which are left over is going to be equal to 8 minus 5. Why? Because I know I started with 8 4s in the numerator, but 5 of those 4s are going to cancel with the 4s in the denominator. So I'm going to take 5 away from 8 to figure out how many 4s will be left over, and that is 3, okay, just like we said over here. So that's where this rule comes from. We're just figuring out how many 4s, or whatever number it is in the problem, are going to be left over once all of that canceling has taken place. All right, now let's look at the next problem over here. We don't want to actually write out 942 7s, in this case, in the numerator, and 947s in the denominator. That would take forever, okay? But if we understand this, then we know what's going to happen, so we don't have to write it all out. We can just ask ourselves, okay, once all of the canceling is done, how many 7s are going to be left over? Well, we have 942 7s in the numerator, which are going to cancel out with 947s in the denominator. So the number of 7s that are going to be left over is 942 minus 940, which is 2. Okay, so once all the canceling is done, there would be 2 7s left. Okay, so our answer would be 7 to the 2nd power, also called 7 times 7 squared, which is 7 times 7, which is 49. Okay, and now let me show you an example with a negative exponent. Again, we have not learned what a negative exponent even means yet. We'll do that in the next video, but I just want to let you know that you can still use this rule here when we do learn about negative exponents, and it will still work. Okay, so for right now, you're just going to have to take my word for it. But how would we do this? Okay, so we have a couple of terms here which we are dividing. The bases are the same, so we can use this rule over here. Okay, and we're going to subtract the exponents. So this would be x to the 29 minus negative 6th power. Okay, this minus came from the rule, and this negative here came from this exponent. So 29 minus negative 6 is like 29 plus 6, which is 35. So we would get x to the 35th power as our final answer. There's no way for us to simplify that further because we don't know what x is. So we're just going to have to leave it like that. Okay, so let's move on to the next rule, which tells us what to do if we are raising a power to a power. So we have some base, which is raised to some exponent, and then we're taking this whole thing and raising it to another exponent. So to figure out what that would be, we would take the base and raise it to the power of the two exponents multiplied together. So the new exponent is going to be the product of the old exponents. So let's take a look at an example to understand why this is the way it is. Let's say we had j to the third, and then we were taking that j to the third and raising it to the power of 4. So what does that mean? That means that we have j to the third multiplied out 4 times. So j to the third times j to the third times j to the third times j to the third. Now, if we unpack that even further and write all these j's out, so each of these j to the thirds is j times j times j, then what would we get? So this j to the third would be these 3 j's over here, and then we have times another j to the third, which is these 3 j's over here, then times another j to the third, which is these 3 j's, then times another j to the third, which is these 3 j's over here. So how many j's do we have when we unpack all of it? We have 12 j's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So our final answer, so this would simplify to j to the 12th. And why do we have 12 j's? Well, hopefully you can see now that it's because we had 4 groups of 3. 4 groups of 3 j's. So if we have 4 groups of 3, then how many is that? And how would we figure that out? It would be 4 times 3 to figure out how many j's we have altogether, right? So that's why we're multiplying these exponents over here, because it's like we have C groups of B A's, or in this case, we had 4 groups, 1, 2, 3, 4, 4 groups, with each group having 3 J's in it. So how many J's are there altogether? 4 times 3. Okay, so I think you get the idea. For this example over here, b to the 40th power, all raised to the 25th power, well, in that case, we would have 25 groups of 40 b's. So 40 b's would be in each group, and there would be 25 groups. So how many b's is that? We're not talking about the bad kind of bees that sting you, luckily. We're just talking about the letter b's, or the variable b's. So how many b's would that be? Well, we wouldn't want to write all of that out, right? But we can figure it out quickly just by doing 40 times 25. Okay, let's do a little mental math here. I know that 25 times 4 is 100, So 25 times 40 would be 1,000. So altogether, if we were to write it all out like we did here with the J's, we would have 1,000 B's. So obviously we're not going to actually do that. We'll just write the final answer as B to the 1,000th. Okay, luckily it's 1,000 letter B's and not 1,000 bees that sting you. All right, and once again, I'm going to give you a couple of examples this time with negative exponents. We'll talk about what negative exponents are in the next video, but the rule still applies when we have negative exponents. We would multiply these exponents together. So y to the 7th, all raised to the power of -2. To figure out what that would be, we would multiply 7 with -2. So 7 times -2 is -14. This would be equal to y to the power of -14. And we might even have two negatives in a problem. That's fine. -7 times -2 is +14. So this would be y to the +14. A lot of students, anytime they see a negative exponent, they assume that the answer must also have a negative exponent, but that's not true. Okay, just following this rule here where we're multiplying the exponents, if we multiply a negative with another negative, then we get a positive. Okay, so you have to pay attention to what you're doing. Okay, now let's move on to the last rule in the video. But before we do that, something I want to point out about the previous two rules is that in these rules, the bases were the same, right? Here in the division rule, we can see we had the same base in the numerator and the denominator. Also in the multiplication rule, we had the same base in these two terms over here. The last rule that we're going to talk about is a rule that applies not when the bases are the same, but when the exponents are the same. Notice over here, I have it written out algebraically. I have C as the exponent in both of these terms here, and also right over here. So for this rule, it's when the exponents are the same, not necessarily the bases. So here's the rule. A number raised to an exponent, like we have a raised to the power of c, multiplied by another number, okay, let's say b, which may or may not be the same as the first number, the first base, raised to the same exponent. So we're talking about having the same exponents here. This would be equal to the product of the two numbers, meaning the two bases, a and b. So the product of a and b means a times b, raised to the same exponent. So I have the product of a and b here, a times b. This is raised to the power of c. Okay, and a similar rule applies for division. So when we have two bases here, which are not necessarily the same, but we have the exponents the same, then if we take this and divide it by this, so we have a quotient here, that would be the same thing as the quotient of the two bases, so a divided by b, all raised to the power of c. Okay, so let's look at an example to figure out why that is. Whoops, we already did those examples. Now we're moving on to these over here. So we have 3 to the 4th times 2 to the 4th. So you can see here the exponents are the same, right? The bases here are different, but we can still simplify this even though the bases are different. We can simplify it because the exponents are the same. And following this rule, that would be the product of the bases. So the product of 3 and 2, meaning 3 times 2, which is 6, all raised to the same exponent that was on both of those terms. So all raised, in this case, to the 4th power. So we would get 6 times 4, which if you actually work that out, 6 times 6 times 6 times 6, that's 1,296. Okay, so we found this by following this rule over here. But where does this rule come from? Why is this true? Well, let's work it out. So 3 to the 4th means 3 times 3 times 3 times 3. I have a string of 4 threes multiplied together. Then times, so I write another multiplication symbol there, 2 to the 4th, which is 4 twos now. 2 times 2 times 2 times 2. Now, everything over here is getting multiplied together. And for multiplication, we have the commutative property, right? The commutative property for multiplication says that the order that we multiply in does not matter. So I can take all these 3s and 2s and rearrange them any way I want. So let's rearrange it like this. All of this is the same as 3 times 2 times another 3 times 2 times another 3 times 2 times another 3 times 2. I still have 1, 2, 3, 4 threes. Oops. And 1, 2, 3, 4 twos. And you know what? Even though I don't have to, I'm just going to put parentheses around these just to make it a little bit easier to read. So what do I have here? I have 4 groups of 3 times 2. In other words, I have 3 times 2, all raised to the 4th power. So hopefully you understand why this is equal to 3 times 2 raised to the 4th power. And this sort of thing would work no matter what the numbers are. You could do something similar here, rearrange everything until you get it to look something like this. So this rule applies no matter what the numbers are. They don't have to be 3, 2, and 4, right? Okay, let's take a look at the next example. So we have 24 to the 5th power divided by 8 to the 5th power. In this example, the bases are different here, so we're not going to use this rule that we learned before. Just like for this example, we did not use this rule. Why didn't we use this rule? Because this rule applies only when the bases are the same. That's not what we had over here. The bases were different. Over here, again, we have different bases, so we're not going to use this rule, which only applies when the bases are the same, right? Same base. But we can use this rule, which we just learned, because the exponents are the same. So, following this rule, 24 to the 5th power divided by 8 to the 5th power is the same as 24 divided by 8 to the 5th power. Okay, now 24 divided by 8 is 3. So we have 3 to the 5th power, and 3 to the 5th power is 243. Okay, so if we do 3 times 3 times 3 times 3 times 3, we would get 243. Now, let's figure out why this is true. Why is this really the same as this? Well, let's work it all out. 24 to the 5th power means 24 times 24 times 24 times 24 times 24. Okay, over 8 to the 5th power means 8 times 8 times 8 times 8 times 8. So I have the same number of 8s down here that I have 24s up here. Okay, now another way of writing all of this is 24 over 8 times 24 over 8 times 24 over 8 times 24 over 8 times 24 over 8. Okay, so now it's pretty easy to see that this is really just 24 over 8 to the 5th power, because we have 5 24 over 8s all multiplied out in a row. Okay, or you could say that 24 divided by 8 is 3, so this is the same thing as 3 times 3 times 3 times 3 times 3, right? Which is what we wrote over here, 3 to the 5th power. Okay, so that's hopefully seeing this, you can understand where this rule comes from. All right, okay, so let's just go ahead and move on to these last 2 examples over here. Now we have this, we have C over here. We don't know what C is, but we could still use this rule to simplify this expression because we have the same exponents over here. That's what you want to look for. So if we have the same exponents, and these two terms are getting multiplied together, then that's the same thing as the bases, as the product of the bases, which would be 72 times c, which we can simply write as 72c, all raised to that exponent, which in this case was 6. Okay, so this is just another way of writing this. Both of these expressions are equivalent to each other. And finally, using this rule, r to the 8th power divided by 2 to the 8th power, that would be the same thing as r divided by 2 to the 8th power. We see that we have the same exponent here, so we can use this rule. The exponents have to be the same. And then we can just take these two bases and divide them. So the base in the numerator divided by the base in the denominator. Okay, and then just take that and raise it to the power of whatever the exponent was. Okay, and that's how we could simplify this expression over here. Alrighty then, so I believe that covers it. Hope you had a wonderful time watching, and have a great day. Bye-bye.